last time I demonstrated how we can program Fourier transform to analyze the signal. Today we're going to use software, Audacity. It's free for doing the same thing and for analyzing these vibrations found in objects. Questions? So if none, let's go to the Audacity app. So the thing is, are you wearing your headphones? Of course, everybody has a microphone, right? So you see here that actually we can record right away any audio. Let me try. Let me see this. Hello, 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 hello. Okay, stop. And let's try and play that. Narinig ba? Ewan ko kung lumalabas yung signal. Narinig niyo ba yun? Okay, nakakapit siya. Okay. Okay, good. Now, what we see here is marami siyang tools. And included sa tools niya is plot spectrum. Is it possible to select as a section? Ayun, pwede. Just drag. Okay. Alright, let's try this. Go to analyze and then plot spectrum. And this is what you see. Essentially guys, ito na yung Fourier transform, yung kalahati ng Fourier transform. And what you see here is the gain. In other words, the gain is parang volume or amplitude yan related sa amplitude or volume, but it is in logarithmic scale. Now, what it tells us is yung low kanina yung sound ko kanina has the following frequencies. Okay? And then nagpipeak siya sa certain frequencies. The peaks that correspond to this would be yung mga dominant frequencies in that sound. Alright, medyo jumbled siya, but can we see pure sound? Yes, we can. Do you have an instrument at home? Try it. Like, I have a guitar. Teka, I'll just pick a guitar and just pluck a string and then let's record that, shall we? Let's do the same for you. Okay, and this is, I don't know if it's tuned, but I'm gonna bring my microphone. I'm gonna have a new recording. Do record, and I'm gonna record a string, just one string. Let's press record first. Okay, and then let's play that. Kung hindi ko makat, i-Fourier transform na natin to. Just the same, lalabas yan. Tools, nasa na tayo? Analyze, plot spectrum. Ano ba? Nakaselect na nga. Ito na nga. What is happening here? Okay, here we are. Analyze plot spectrum. There you go. Okay. Now, unfortunately, the rest of the spectrum that you see here are all the background and all the silent parts and all the other things. But what I want you to see is this peak. Ano ba tong peak na to? The peak is here. Lumalabas yung value ng peak dyan sa baba or sa cursor. So, it's at one peak is at 394 Hertz. Nakikita niyo yan, yung G4 na. It's very nice because it indicates kung ano it even says kung anong klaseng note yon, right? Now, ito yung use ng Fourier transform because essentially a sound wave is a pure tone. If we zoom in on this part here, you see nagmumukha na siyang sine wave. What you see here, oh? That's the sine wave. That's the guitar sound. Okay. Alright. Pwede bang tumaas to? Alam kung paano pagkasin to. But you can see the sinusoid showing up. Okay? And there would be perhaps some other harmonics in the mix. But the dominant frequency would be whatever is the sinusoid. Naalala nyo yung last time, nag-Fourier transform tayo ng sinusoidal, artificial sinusoidal signal, and then we see a peak. The same goes here, except that this is displayed as logarithmic scale. Okay? So, but this indicates yun yung peak ng sound, and this is the dominant sound that you will hear. So, whenever you see a spectrum plot, and then you can see the frequencies that are there, and there is one that stands out. Like here, now, this is right now at log, no, this is log frequency. Kasi naka-log, ito yung log frequency, no? So as you can see, it's in log scale, so 50, 100, and then 1,000, and so on. If this y-axis was made linear, makikita mo, ito yung medyo dominant sa lahat. The rest are small. Nakikita lang sila dahil medyo ang log scale, pinapakita pati yung mga tiny signals around it. Which means, kapag naggawa tayo ng other tone, lilipat yung frequency na yun. So now it's at 394. Let's record another one. Press record. Stop. That was the lowest E in the guitar. Okay, that's the thickest string. Then let's analyze that. Okay. Analyze, plot spectrum. Oh, so select. Oh, what's that hand there? Oh, what's this hand? All of a sudden, there's this hand. Okay. Ano ba? Control A. Okay. What was that hand? All right. Let's see. Ayun. Siya naman ngayon, this one is the highest of all the peaks. And if you can see here, look, oh. You go down and look at the peak kanina yung nakasulat dito. Watch this here. As I move the cursor, you can see it's E3, 160 hertz. Okay. There. That's the peak around that region. Okay. Now, and that means itong E string na to, if we zoom in again, you see the sine wave, and this frequency of that sine wave is 164 hertz. It's not a pure sine wave. You know why? Because there are additional waves that are in that give the guitar its unique tone. And so if you have a different instrument, merong dominant sine wave, and there are some other small sine waves that give the sound its characteristic tone. So if you do this for a violin, harmonica, trumpet, you play the key of E or do, re, mi, but yet there will be a dominant note E, but there would be other sine waves, as we have seen in the spectrum, like these, no, that contribute to this shape, which is not purely sinusoidal. Okay. Now, paano niya napaplot yung spectrum na alam niya ito yung problem natin last time, di ba? Pag tayo yung gagawa ng Fourier transform, dapat alam natin yung sampling. Well, guys, yung sampling nito is over here. Do you see this? Project rate. This is 44,100 Hertz. And that's the highest. Naalala nyo last meeting, yung sinabi ko that we humans can hear at 22,000 Hertz. Nyquist sampling theorem says if we want to record up to 22,000 Hertz, our sampling rate should be twice as fast. So that's why 44,000, tas nagdagdag pa siya ng extra 100 Hertz para pasok pa rin yung mismong 22,000. So when I record audio, it is recording at in 1 second, it is sampling 44,100 time samples of this, or sampling it at that frequency. Okay, in 1 second, ito yung samples niya. Okay, taas. Of course, this can be changed. Okay, and so you can choose this. The lowest, guys, is 8,000. Alam niyo kung bakit? ito na yung next lesson natin. Bakit 8,000 yung isa sa mga choices? In fact, we can go beyond. Kaso ito, baka accelerometers na ito yung tinitignan dito. Alam nyo ba, ang mga cellphones, sometimes, pag cheap lang yung cellphone, ang sampling nila ng audio signal mo ay 8,000. Digital devices na nagre-record. 8,000. Bakit ganun? Well, let me show you our next lesson, of course. Now, if you go and I search for uh, frequency response, okay, and then we look for the images. So ito nga, now we can hear from 20 to 20,000, sabi ng iba, 22,000 hertz. Okay, let's pick an image. Short. Okay. Frequency response of human ear. Okay. Tayo, alam niyo ba guys, this is a frequency response plot. It tells how sensitive our hearing is to various frequencies of sound. Yes, we're sensitive. We can hear from 20 hertz to 20,000 hertz. Above 20,000 hertz, wala na tayong 22,000 hertz na tayong rinig. Below that, wala na rin. Masyado nang bababa. But our peak sensitivity is at 3,000 hertz. Meaning, if somebody plays a tone at 3,000 hertz, rinig na rinig natin yan. Okay? That is the reason why yung mga cellphones na luma or mga cellphones na cheap lang, they go a little bit over this and sample and say that, okay, they will cut off here at 4,000 hertz. So, kumbaga, hindi na nila i-capture yung mga signals na posibleng high frequencies. So, if they just want to capture signals na up to 4,000 hertz, how much should they sample? They should sample at 4 times 2, which is 8,000 hertz, or 8,000 samples per second. All right? Or 1 over 8,000 of a second. Okay? And we know that we validated that because we measured the frequency response of several phones during one of our projects, and we found that it's mostly 8,000 hertz. How do you measure the frequency response of a system ba? Well, there's many ways. And again, another activity. Normally, ang gagawin nyo guys is kunyari, nasa laboratory tayo, meron tayong frequency generator, meron tayong microphone, or meron tayong device na nakaka-measure ng vibration. Isa-subject natin sa vibration yung object at a certain frequency, tapos meron tayong naka-attach na device na nagme-measure ng vibration niya. Kung kunyari, yung power ng vibration natin is this much, pero yung na-perceive nating amplitude ng vibration ng object is this much. So, bali, iyon yung magkakaroon ng ratio. So, the ratio would be displayed in this log plot. You understand? So, kunyari, yung amplitude ng vibration is 5G, pero yung nare-recover nating amplitude of vibration is 3G. Kukunin natin yung ratio nun, tapos iyon yung i-log scale natin yon. For that frequency, ipa-plot natin. And we do it one time per each frequency until we recover this plot. That's kind of tedious, right? But there is another way. The other way is to subject the sample to the range of frequencies in time. No? Yun, pakitaan mo siya ng uniform ng signal that has frequencies in a certain range of uniform power. Okay? Then, i-record mo kung paano siya mag-vibrate. Okay? What does that mean? If you were to measure the frequency of that test signal, mukha siyang flat dito. In frequency space, flat siya. Kasi, it contains all the frequencies in equal power of the frequency range that you want to test. Okay? And then, so, yung signal na yon na ang itsura ng frequency response niya ay uniform in frequency space, meaning pare-pareho ng power dito sa mga range of frequencies nito. Okay, palagay natin 1K to 1,000, 1K to 10,000K uniform power. This much power ang isa subject mo i-play mo na sound. When you say power in terms of sound, that means volume, no? So same volume, no? You will have a signal from 1K to 10K of the same volume. Okay, normally you will do that 1K, 2K, 3K, 4K, 5K, and then just measure the vibration of the sample to see kung meron siyang ganitong klaseng response. O meron siyang, nagpitik ba siya at a certain frequency. But, it can be done in a single shot using the chirp signal. Now, let's go back to Audacity. It can generate test signals. Go here. Do you see this? Generate chirp. You can tell kung ano yung, so the chirp, well, you can have it square, sawtooth, but of course we want to have a sound wave, so sine, and then you can tell it to start and end, and kung ano yung amplitude. So let's say, let's start at 100 hertz, and say, let's just end at 3000 hertz, okay? Well, we can leave the amplitude at that. And then we can change the duration, like this is in 6 seconds. So, medyo matagal to. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000. Medyo mataas to. No? Let's reduce the, the amplitude. Baka kasi matinis masyado. Okay? Okay? This is uniform power, okay? So, pag 0.5, 0.5, it's uniform power to. Okay, let's just see how, so it will generate that. Let's have it generated. And here's how it looks. As it goes in time, mag-i-increase yung, ano niya, yung frequency niya. Okay? Let's look at its spectrum. Here is its spectrum. It's very nice. Look, oh, at 100 hertz, it starts to plateau. And at 3000 hertz, yan. This is frequency response, guys. So this is frequency. So, syempre, it rises, it tries to rise, and then this is it. So if you subject your sample or your object to this signal, and it's called the chirp signal, it's like you're subjecting it to a signal with a uniform volume of varying frequency. How does it sound? So for 6 seconds, it sounds like this. Ouch! Did you notice that it's sounding louder and louder as it goes to where were we na? Sakit sa tenga. 3,000. Malapit na tayo sa mag 1,000. It's gonna get louder as it goes. And that's because we're very sensitive to 3,000 as we go to near 3,000. So let's shorten that. Let's generate again, but let's shorten the chirp. Instead of 6 seconds, let's have that. Let's have it 3 seconds. Okay? Okay. So let's listen to this for 3 seconds. Bear with me, guys. Ah! You hear that? Ouch. But yeah. So, ganun ang itsura ng, that's how a chirp sounds, no? It's parang increasing, indeed, you notice that there's an increasing frequency. But what's nice about this is that if you subject your object or your machine, for example, to this kind of vibration signal, you can detect if your object resonates. What again do we mean by resonate? Something that resonates is something that vibrates at a certain same frequency. Something has a natural frequency. Kunyari, any string tied at both ends will have a natural frequency. Okay? So, kunyari, itong E string ko, okay? That's how it sounds. That's the natural frequency, 164 hertz. Okay? The last E string here, okay? The last part of the string, let me show stop share muna. And I'll show my video. Share video, start video. Okay. Alright. Bakit blurred ang aking background? Video settings, video filter, choose before background. None. Okay. All right. If you have a guitar, if you play a guitar, the last thin string is E. But when you tune a guitar, you can choose another point here, that other string, di ba? So, you can actually make one of them resonate. Meaning, if you play one of these strings, they sound the same now. These two last strings, this one and this one now sound the same. So, you try this if you have a guitar at home. Put a piece of paper, tissue paper, folded in half, tiny, tiny tissue paper on this string, and then pluck this string. And just pluck one of the strings, and on the other string, put a tiny tissue paper. You will see that the other string resonates if the tissue paper vibrates. Okay? It can cause resonance. Okay? So if they have the same natural frequency, you play one of the strings, the other will resonate. Now, this resonance thing, I'll stop video and share the screen. Now, this finding of a resonance of an instrument, device, or what have you is very important. Why? Because for a guitar, we want to see if it can resonate the sound of the strings. If it resonates, then it will make the sound louder. And that's the purpose of the sound box of a guitar. Okay? It will make the sound appear louder because nagre-resonate yung sound box. However, for another application, such as satellites, well, actually kahapon guys, alam niyo ba, galing sa isang company yung team namin kasi binibration test nila yung camera to see if it resonates somewhere. In the case of the objects that we sent to space, we want to find kung ano yung resonance, natural resonances or resonant frequencies ng ating satellites. Why? Because when you send it over rocket, nagbabibrate yung rocket eh. And malay natin, yung vibration ng rocket as it travels to space matches one of the natural frequencies of the satellite or its payload. Problema yan. Kasi mangyayari, they will resonate. Magbabibrate yung yung camera or yung satellite. And what happens pag nag-vibrate siya? Baka mamaya magkalas-kalas yung When the resonance is strong, there's a tendency na baka sobrang vibration ng object may ma-dislocate na part. And that's disastrous because once the satellite is up there, we can no longer bring it down to fix it. Okay? So that's why even before a satellite is launched, check na kung nagre-resonate ba siya in the same, if it has the same frequencies of resonance as the rocket that will be used to launch it. And so, how do you do this, say, for your machine? So, kunyari, meron kayong, if you don't have a guitar with a sound box, you can create your own sound box. It's any kind of box. And then, pwedeng tissue box. Tingnan natin kung magre-resonate siya. And then, just generate this chirp sound. And put a microphone. Say, for example, put the microphone and see kung ano yung kalalabasan ng chirp sound na yon dun sa sound box. So, and let me demonstrate again. How do we do a resonance test on a sound box? Let's go back to Zoom. And Zoom, come on Zoom, stop sharing. Okay. So, here's the camera. Here's the camera. Here's the guitar. Here's its sound box. That is my computer. I'm looking at my computer. It's generating audio from Audacity, the chirp sound. Yeah. Now, well, from another, you could have the audio from another machine, no? Then you put a microphone or an accelerometer on the machine or the instrument. Okay. So if you have another object that can generate a chirp sound, like a smartphone, okay, play that put the microphone in the soundboard, click record, and take a look. Now, since you're sure that the signal generated has uniform volume, what you want to know is the recorded volume in the uh, guitar uniform as well. If we see peaks, then those are the resonance peaks of the soundboard. Do you understand? So first step, prepare a chirp signal, have a machine generate the chirp sound. Okay? Play the chirp sound while having a microphone attached to, or an accelerometer in the case of instruments, attached to the instrument or the soundboard or anything that you'd like to see if it's resonating. Record the vibrations from the soundboard while the chirp is playing. So it might happen that you also hear the chirp, but it's okay. What we want to see is if the sound recorded, when we take the spectrum or the Fourier transform of the sound recorded from your guitar, we'd like to see if there are peaks. Okay? Okay. Now, I don't know if I can record and play simultaneously. So, let me see if it can happen na kasi baka hindi pwedeng mag-record and play simultaneously. So, what you can do is you can perhaps download an app that can generate a chirp signal. And then you can have that as the source, vibration source, and your Audacity as the recorder. Okay? And then what you do, you record that, you display the spectrum, and you look for peaks. Yon. And if you see peaks, that means that your sound box is resonating. If the peaks are not so clear, that means hindi nagre-resonate. Kunyari, medyo flat rin lang yung spectrum na nakukuha mo. It means konti lang yung, or minimal lang, or low, wala halos resonance yung sound box or structure. Okay? Anything can vibrate so long as it's free to move. Okay? So even the walls of your house, 'di ba? Panapansin niyo pag kumukulog minsan uuuga yung yung dingding niyo. That's a manifestation of resonance. Okay. Okay. Next, I move on to this other. May tanong ba tungkol dun sa resonance experiment? Any questions about how we will do the resonance experiment? You don't need an Arduino for this. You just need Audacity, your earphones. If you don't have a musical instrument, any box can do, like a plastic box, no? Just to see if it resonates. No? A plastic box will do. Okay? And lata. Yes, yung mga cavities, any cavity-like structure, mga baso, mga lata, yan. Pwede nating makita kung nagre-resonate sila. And that's it. Can be done. Okay, I'll move on. Bakit nagkakaroon ng resonance? Okay? And this is the physics of it.